In this video, we're going to cover some of the material that's in Chapter 10. We're going to extend hypothesis testing about the mean to hypothesis testing that compares the means across two samples. So before we had just one sample, we had one population parameter that we were interested in testing hypotheses about, mu, the population mean, and now we're going to have two different populations, so we're going to have two different samples. We're going to compare or test hypotheses about the equality or difference between the two population means using sample data. So we need these subscripts that will stand in for us for the two different populations and the sample that we pull from those two populations. I'm going to consider the examples where the standard deviations are unknown and they need to be estimated from the sample data. That's the more complex example in this case because we need to use the t-distribution, and there's a formula that we need to cover in order to calculate the degrees of freedom. If you have a very large sample, or if you know the standard deviations of the populations, then you won't have to use the degrees of freedom formula. You'll be able to use the standard normal distribution. So there are three types of hypothesis tests again. There's left-tailed, there's right-tailed, and two-tailed. I would point out first that the equality always shows up in the null hypothesis again. And the way that we write the null and alternative hypotheses is such that the zeros always show up on the right-hand side of the hypotheses. So when you look at it, you kind of rearrange the inequalities in order to really understand exactly what the null and alternative hypotheses are stating. For example, if you look at a left-tailed test here, the null hypothesis says that mu1 minus mu2 is greater than or equal to 0, but it's easy to just rearrange that and see that the null hypothesis is that the mean in population 1 is bigger than the mean in population 2, and the alternative is that it's less. And in this case, for a right-tailed test, the null hypothesis is that population 1 has a smaller mean than population 2. And just another way of saying that is that the difference between mu1 and mu2, mu1 minus mu2 is less than or equal to 0. And the alternative, of course, is that the difference between the two means is positive, or that the mean in population 1 is bigger than it is in population 2. For the two-tailed test, the null hypothesis is that the two means are equal, or that there's no difference between them. And then the alternative is that the two are not equal to each other, so that mu1 is not equal to mu2. So we need a test statistic, and in each case, just like before, you will use the same test statistic, and whether or not we reject the null hypothesis or fail to reject it will depend on the value of the t-statistic that we calculate. And we'll be comparing that to critical values or calculating p-values for it. In the numerator of the t-statistic is the estimate of mu1 minus mu2, which is our best guess, which we find just by taking the sample means and plugging them in for the mu's. So our best guess of the difference between the population means is the difference between the sample means. So there you go in the numerator. And of course, we need to standardize that point estimate. So this is really our point estimate, and we need to be concerned with the sampling distribution of the point estimate. And the sampling distribution of the point estimate, what we need to know is we need to know the standard error of that estimate, and that is given by this formula in the denominator, which looks a lot like the formula for the standard error of the estimate for the case of a single sample mean. Here, S1 squared is the variance associated that we estimate for the first population from the sample data. S2 likewise, S2 squared likewise the variance that we estimate for the second population from the sample data. And then in order to get the standard error of the estimate, we divide each one by their respective sample sizes, add them up, and take the square root. Of course, this is a t-distribution, so we have to think about the degrees of freedom, and it's not quite as simple as just taking n minus 1 this time. And the sample sizes could potentially be different. We've got to think about how to weight the degrees of freedom for x1 bar versus x2 bar and their sampling distributions. So it turns out that the sampling distribution for the test statistic that we've calculated on the left here, right? So taking the point estimate of x bar 1 minus x bar 2 and dividing it by the standard of the estimate gives us a sort of a standardized t-score that we can compare to different values in a table or look them up on a computer. But to use that, we need these degrees of freedom, and this turns out to be the formula for calculating the degrees of freedom for that t-distribution. We know everything that's in the formula, even though the formula looks kind of cumbersome. We know how to calculate the sample variance for a population. We have to do that twice, and we have two population sizes, N1 and N2, but those are really the only parameters that we have to kind of plug into this equation and then follow the order of operations. It is a little bit more of a cumbersome formula, so I would highly recommend using a computer to do this, and you should really know how to use the tools in the data analysis toolkit in Excel or some other type of a software package to complete this type of a hypothesis test. When the calculations get a little bit more complicated by hand, the opportunity to make a simple, error or mistake kind of creeps in there. So in order to demonstrate the way that this works, I'm going to use this example of PAR Incorporated. We're going to pretend here that we're a manufacturer of golf equipment, and we designed a new golf ball. And we want to make a statistical claim that our golf ball has better driving distance than our competitor's golf ball, where our competitor's is RAP. They're our closest competitor. And so we're going to collect two different samples, one from a population of our golf balls and one from the population of our competitor's golf balls. We're going to take them out to the driving range. We're going to hit all the golf balls. Right? And we're going to hopefully hit them under the same conditions, right? So we have the same person driving the golf balls with the same clubs on the same day, etc. And the only difference between the driving distance for the two samples is the fact that we have two different sets of golf balls. And we're going to measure the average distance in both cases. And we're going to compare the two with a hypothesis test to see whether or not we can make a statistical claim that we have a better golf ball. So we want to put the burden of proof against ourselves, and step one is always to state the null hypothesis. So we're going to state the null hypothesis as the straw man, and that basically what I mean is that we're going to assume to begin with that our golf ball is no better than the competitor's golf ball. So the null hypothesis is going to be that golf ball 1, so the first population is going to be our golf ball, and the second population will be the competitors. And our null hypothesis is going to be that our golf ball is no better than the competitors, that our driving distance is less than or equal to our competitor's driving distance. And then the alternative will be that we actually have a superior golf ball, and we're going to have to really get a lot of sample evidence in order to make our claim. So again, our desired research result shows up here as the alternative hypothesis. So that implies a right-tailed test, of course, given that the first population is our golf balls and the second population is our competitors' golf balls. What we would like to show is that our golf ball has an average higher driving distance that's greater on average than the competitors. In other words, mu1 is greater than mu2. That's what we'd like to show, so that's our alternative hypothesis. So our null hypothesis must be that our golf ball has a driving distance on average that's less than or equal to the competitors, and that of course implies a right-tailed test. We're going to reject the null hypothesis if the difference between, in the samples, if the difference between the driving distance from our golf ball is larger than the driving distance of the competitor's golf ball by a large enough margin. Okay, so we've set up the null and alternative hypotheses, and then we're going to take a break here. I would like you to formulate the null and alternative hypotheses for the video lecture checkpoints. Before you jump in, just make sure you have a number of things open in order to complete this lecture. I'm going to ask you to do the calculations in Excel. So if you're not familiar with how to do these types of hypothesis tests in Excel yet, you should review the Excel guide that comes at the end of Chapter 10 and 11 notes and Excel guide. In every set of chapter notes, I give you very careful step-by-step guides of how to do the different procedures in Excel. And to complete this exercise, I would like you to review that Excel guide, open up the dataset mutual.xlsx, and answer the checkpoint questions. What you're going to do with mutual.xlsx is you're going to compare the mean return on two different types of mutual funds, what are called load funds and no load funds. And we're going to formulate a hypothesis that tests the equality appropriately. It's going to be either a left-tailed, right-tailed, or two-tailed test. You need to make that determination when you read the case study. But we're going to go all the way through a hypothesis test that looks and compares the means between of return between those two different types of mutual funds. So open that up, read it carefully, read the case study carefully, and see if you can answer this first checkpoint question. Okay, so hopefully formulating the null and alternative hypothesis for the checkpoint questions wasn't too much of a problem. Now that we've formulated the null and alternative hypothesis for the example that we're working through in the video, which is the golf balls, what I would like to do is talk about step 2, of course. Step 2 is to pick a level of significance. I'm going to set the level of significance to 1%. So I'm only willing to make take a 1% chance of making a type 1 error, or claiming that I have a better golf ball than my competitor when I really don't. So there's step 2. Step 3, you know, is to collect sample data. And from the sample data, we'll need our point estimate of the difference between the two means, the standard error of that point estimate, okay? And then from those two pieces of information, we'll calculate our test statistic, right, and our degrees of freedom. So this is kind of the more intensive part in terms of doing the calculations. And so we go out and we get 120 of our own golf balls, and we get 80 of our competitive golf balls. So there's N1 and N2, the two sample sizes. We drive each one of the golf balls under the same conditions, and we find that our golf balls in the sample have 275 yards as the average driving distance. We have 258 for our competitor. We calculate the sample standard deviation. That's our best estimate of the population standard deviation. We get 15 yards for our golf balls and 20 for the competitor's golf balls. Okay. So here's X bar 1, here's X bar 2, here's S1 and S2. These are all the elements that are going to calculating the value of our test statistic. That happens on this next slide. So the difference between our two driving distances, back just a second, 275 minus 258, that's 17 yards. Okay, the question is that a big enough difference given the fact that we're dealing with a random variable, X bar 1 minus X bar 2 is a random variable? Is that a big enough difference to conclude that we actually do have a better driving distance for our golf ball if we're willing to only make a 1% chance of claiming that we have a superior golf ball when we really don't, right, making a type 1 error. So again, all we have to do here is plug in the sample sizes of 120 and 80 and our standard deviations that we reported in the previous table in the appropriate places in the formula for the standard error of the estimate, the estimate being the difference in the two means. And we get a value of 2.622. We're going to take the ratio of 17 to 2.622 in order to measure that difference between the means in terms of standard deviations, right? So when we take 17 divided by 2.622, what we find out is that we're 6.483 standard deviations, right? The difference between the two is 6.483 standard deviations from 0, basically, okay? So that's the value of our test statistic. And then, of course, we have to plug the right numbers into the degrees of freedom formula. So we've got our standard deviations again that we read off the table for S1 and S2, and we've got our sample sizes that we plug into the formula. We put all of those in the right places, and those are the only 4 parameters we really need to look up and plug in, and we follow our order of operations, or preferably use a computer to do this for us so we don't make a mistake. We really want to do this, even this on a handheld calculator or something. And we get an answer of 136.6. So that's our degrees of freedom. We're always going to round that down. That's sort of a conservative approach, is just to round that down. So we'll use a degrees of freedom of 136. So here's your second checkpoint question. Okay, step 5 then is just to determine whether or not we're going to reject the null hypothesis. Clearly, in this case, we have a right-tailed test, so a very large value of the test statistic is going to reject the null hypothesis for us, and we'll be able to conclude that we have a superior golf ball. So using the p-value approach, again, I don't really need to provide a lot of additional information. You should be able to draw these pictures now for yourself. Using the p-value approach, we can go to a t-distribution with the appropriate degrees of freedom. That is 136 degrees of freedom. And we look at the area that's left over, of course, in the right tail at 6.438. Why in the right tail? Well, because this is a right-tailed test. And it's a large value of the test statistic in a right-tailed test that rejects the null hypothesis. I would expect that you would be able to perform this type of a test and construct the p-value correctly and interpret it if you had a left-tailed test or even a two-tailed test. But this is a right-tailed test. So at that value of our test statistic, we only have 7.6 e to the minus 10th area left in the right tail. It's a very small number. So we say we have a very significant test statistic. Since 7.6 e to the minus 10 is definitely less than 0.01, we reject the null hypothesis. So at the 1% significance level, we can conclude that we have a superior golf ball. We can also use the critical value approach. All we have to do with the critical value approach is go to a t-table, look up in the t-table, or you can use an Excel function to do this. Look at a t-distribution with 136 degrees of freedom. Okay, and look for the critical value for a 1% level of significance in the table, and you'll find that the value is equal to 2.354. Using the critical value approach, 6.438 is bigger than 2.354, so we reject the null hypothesis again. And really, again, these are just two equivalent methods for testing the null hypothesis and making a conclusion, and it's just a matter of which one is more convenient. And it's to some degree a matter of preference which one you use. Here is your additional checkpoint questions.